Hello, welcome back. Today we're going to talk about CUDA mixture of experts and training. So for those that don't know, like nowadays for modern LLMs, they're typically transformer based. Within a transformer, you have attention and then you'll have a feed-forward network. Feed-forward networks are really great because they allow you to do feature extraction, but they're also very computationally expensive. So in practice, what happens in modern models is we do mixture of experts where we kind of shard this FFN. And then when we have a token, we actually send this token to a small subset of the FFNs. And the basic intuition is that the model is going to learn how to route tokens accordingly. So for example, if you have a math-related token, it will know to send that token to the math-related experts. Now, one problem with this is you end up having imbalanced routing, where different experts, different feed-forward networks are going to get different amount of tokens to process. And so that's an architectural challenge, especially once we talk about CUDA graphs. So what is CUDA graphs? So CUDA graphs is this really great way to reduce CPU overhead. And the way it works is you record a graph. So you tell the CUDA graph API, hey, I want to record a graph. And then you launch a bunch of kernels. And then you say, hey, CUDA graph, stop recording. And then if you copy, and so for your next batch, if you copy your tensors into the static memory addresses of the input to the CUDA graph, and you run the CUDA graph again, it's going to skip all this overhead and it's going to run your kernels consecutively. And then you can read from the static output addresses. And so in practice, especially with the most modern GPUs, where there's high CPU overhead, we basically want to make sure we can CUDA graph our training. And then just as an aside, people oftentimes like to talk about host-to-device syncs. I just want to make it clear that a host is basically your CPU and device is your GPU. And sync means that they're going to communicate. And generally, you want to reduce syncs because it slows things down. Ideally, you invoke something like a CUDA graph. It just completely on GPU runs all of its computation and then gives you back the output. You don't want it bouncing back and forth because that's a lot more inefficient. So let's talk about how to implement a mixture of experts. The first way is via host-to-device syncs, where you do your dispatch, or in other words, figure out which tokens route where. You come back to your CPU, and then you dispatch dynamically to your experts. So this is pretty good for memory because you're just allocating precisely what you need, but it's bad for performance because you have this host-to-device sync. So one way you can avoid the host-to-device sync is to do worst-case buffers, where you basically allocate a buffer for every single expert that is the worst case, like as if all the tokens got routed to it. So with this, you have complete static addresses that you can CUDA graph, but it's bad because you end up wasting a lot of space, and you're probably going to So the most modern way is called page stashing, and the basic intuition is you're going to allocate a single buffer that represents the worst case token routing, but you're going to reuse this buffer across your layers, okay? And the basic flow is as follows. You're going to do your dispatch, and that dispatch is going to insert tokens into this buffer. You're then going to call your expert, and you're going to call your expert with the amount of tokens because you know this number because it's on your GPU. So your expert is just going to read from your worst case buffer the amount of tokens that you pass to it, and then it's going to calculate activations, and it's also going to calculate outputs for the expert. Now, when you're doing training, saving the activations is important for the backwards. And so what you're going to do is you're going to save your activations via this stash stream into what's called a shared page pool. And this shared page pool is just going to have all the activations you had during your forward. And what you're going to do is you're just going to save kind of like a pointer into this page pool for backwards. So once you come to backwards, you can use this pointer to basically get the activations to be able to do the backwards. And yeah, so this kind of like captures it, basically by using this combination of worst case buffer with this page pool, you can basically have everything on GPU, everything with static addresses, and you kind of have the best of both worlds. So yeah, that's all I wanted to cover today. Hopefully that was interesting. If you are curious, there's this pull request in Torch Titan 2712 that actually implements this. So I highly recommend you check that out. But yeah, I'll see you in the next one.